Now, if we have a uniform magnetic field, let's say that we introduce a charge somehow into this magnetic field, since the force is always perpendicular to the velocity, that's going to create a curved path. If the field is uniform, then the force is a constant magnitude. It's changing direction, but it's a constant magnitude. And that means that we'll get circular motion. So again, if we have a charge moving through a magnetic field, we can end up with circular motion within that magnetic field region. And here, I guess they're saying this is the path of the electron. So let's see if that works. Let's see. It's an electron, it's negatively charged. I'm going to use my left hand. There's the velocity direction. Field is into the page. And so, yeah, the force is in that direction. And as we go around the circle, we just keep redirecting the velocity, and that redirects the force. So we maintain that circular motion inside of the magnetic field. So here's an example. I think it's the example on that previous page. I might have changed some numbers, so check and see on that. See if that might be happening. Get the arrow out of the way. All right. Here is, it's negatively charged. Here's a negatively charged, oh, it's positive, sorry. It's a positively charged particle. There's a magnetic field. And what's happening is, here's the velocity, here's the force, and they just stayed perpendicular the whole time. Here is the center of that circular motion. Now this is always a little, I don't know if it's mysterious, but we're used to thinking if there's something at the center, that's what's creating the force. You know, it's like the sun is here and the earth is orbiting and there's a gravitational force and it's coming from the center. This time there's nothing at the center that's creating the force. The force is being created locally due to the magnetic field. Now, even though there's nothing at the center of this circular motion, we still need to identify where the center is in our diagram. So for example, if it's circular motion, there's going to be some radius of curvature for that circular motion. Let's see if we can derive a formula to tell us what the radius would be for the circular motion that we're going to end up with. First of all, from way back, chapter 5 I guess, we derived this formula showing that whenever something is in circular motion, A is to V is to R. And that gives us this formula right here. Now that's just kinematics. Then we said, aha, here's the law of motion, says that motion, acceleration specifically, depends on the force and the mass of the object. So the force we're going to get here is Q, V, B. And I know this is new, so this is, you know, you get it in your practice, but these are the new force formulas that we've got. So this is the force acting on a charge, moving with velocity v through magnetic field B, where the velocity and magnetic field are perpendicular. And then here's the mass of the proton, I hope. Yeah, the mass, I got the right mass. So here's the proton charge. There is the proton's velocity. We're in a field of 1 Tesla. I think I made up these numbers. And then that's the mass of the proton. Anyway. Let's see, I can take my motion equation and my force equation. They're both acceleration equations, and I can piece those together. That gives me v squared over r is equal to qv over m, and then after wandering around in a couple of algebraic lines, I end up with this. It says, hey, look, this is going to be the radius of the circular motion for a charge, an object, a particle with mass m, traveling at speed v with a charge q in a magnetic field of B. You go, really? That's kind of interesting. I can see those 4 effects. What it's saying is if I send this charge into a magnetic field it's going to end up in circular motion if the field is uniform. And if it's heavier, if there's more mass, the radius is going to be larger, right? A heavier object is more difficult to redirect. And if it's going faster, that also makes the radius bigger. In fact, you can look at that top mv and you go, that's kind of like momentum. The more momentum it has, the bigger the circle is, the harder it's going to be to redirect it, if it's got a lot of mass or if it's going at a really high speed. What is it that would give us tiny circles? Well, the tiny circles come if there's a lot of charge and a large magnetic field. You go, oh yeah, that makes sense. If there's a lot of charge and a large magnetic field, that's going to create a large force, and that will tend to tighten the radius. And so for the particular set of numbers that I picked out, the 1 Tesla, 2 times 10 to the 7th, and then the charge and mass of the proton, I ended up with 0.20 meters, or about 21 centimeters. So for those particular numbers, I'm getting circular motion of my proton that looks something like this. Now, in order to maintain a circle that closes on itself, I have to be careful about how those protons get introduced to the magnetic field. They have to be moving perpendicular. If I don't do that, if I actually tip it a little bit, then instead of getting circles, I'll get a spiral. But hey, spirals are cool too, right? So the circular motion will be happening, but then there'll be a drift in whatever direction is along the field itself. Okay, so we've got a force on an electric charge moving in a magnetic field. Things to remember here, the magnetic force is perpendicular to the magnetic, here we go, magnetic force is perpendicular to the magnetic field direction. So whatever direction the magnetic field in, the force is perpendicular to that. It's also perpendicular to the velocity. Now the right-hand rule is useful for determining directions, and we've kind of slipped a few left-hand rules in there also. So you can also think about doing that. The equations in this chapter, I think number 3 is very important. What happens is, once we've got the diagram set up, using left and right-hand rules, once we've got the diagram set up, it's the diagrams coming from the right and left-hand rules that give us the direction. And the equations then will drop the vector signs, and the equations will just be giving us magnitude. So those become 2 separate things to keep track of. Keeping track of magnitude versus keeping track of direction. That's been pretty common since all the way back through Physics 4A, but here I feel like it's going to become even more important for us to keep track of that. All right, here's a bunch of right-hand rules that the book uses. Again, I'm using a different convention, so you can take a look at those if you want and decide. Here's what we were talking about before. If I have a charge, an electron or proton moving through a magnetic field, what will happen is I'll end up with these loops, circular loops, around the magnetic field lines. If the magnetic field is getting stronger or weaker, those loops will get tighter in regions where the magnetic field is larger, and then they'll spread out a little more in regions where the magnetic field is not as large. And then I'll end up with kind of this drift, whatever velocity the charges have in the direction of the magnetic field. The object will just tend to maintain some drift velocity as it spirals around those magnetic field lines. All right, that is probably a good place to stop for our lecture number 1 for this chapter. Ooh, let me go back one. We'll come back and we'll pick up with this in the next lecture. All right. All right, so here's kind of where we left off. So we had been looking at magnetic fields and looking at charges traveling through magnetic fields, and said that in magnetic fields it's possible for these charges to kind of get trapped because they end up with this sideways force. So they end up making these loops. If it's a uniform magnetic field, those loops are circular, and you can end up with these effects where you end up spiraling these charged particles, spiraling through magnetic field. And so here's an interesting example of that. These are the aurora, not just the northern lights. The borealis is northern, the australis is southern. But we end up with these auroras as a result from Earth's magnetic field. So Earth's magnetic field is kind of interesting. It ends up redirecting particles that are coming in from the sun, the solar wind. So with all these violent reactions going on in the sun, also magnetic effects there, a lot of charged particles end up coming off the surface of the sun at pretty high speeds. So here you've got a bunch of high energy electrons and protons that are coming in towards Earth. And what will happen with those charged particles as they approach Earth is they're going to get redirected by Earth's magnetic field. So they're showing some of Earth's magnetic field lines here. Here is a proton or an electron. We could stop and use some right-hand rules to figure out from the looping direction. Let's see, I'm going to say it's a proton from the direction of looping, see if that matches the right-hand rule. So we've got these loops, and these get caught up. Now remember what we said is, as the magnetic field gets larger, the radius of the motion, of the circular motion, gets smaller. So you end up at first with larger loops for these protons and electrons coming in, and then they get tighter and tighter as they follow the magnetic field lines. And the magnetic field lines redirect those charges away from the mid-latitudes, and so that most of these charges are entering Earth's atmosphere or coming in towards the Earth from near the polar regions. And as these electrons and protons, I think it's primarily electrons, are following these circular paths, they also radiate light. So when I have these charges in circular motion, they're accelerating. That's an acceleration. And so these accelerations actually lead to radiating electromagnetic fields that propagate away. It's actually light. So accelerating charges generate light. And that's what we're seeing with the auroras here. So interesting effect. Now, there's also the same effect towards the southern, right? If charges are coming in the lower regions, those charges are going to get directed in towards the southern portion of the planet. So it does have an effect on sustainability, I guess, of life. With the number of protons and electrons, high energy particles coming in, it could damage the atmosphere. This sort of having a magnetic field does make a difference for the planet. Here are forces acting on an electric charge moving in a magnetic field. So let's take a look at this too. So here is here's a charge coming in. It's coming in at some velocity. Here is an opening that we've generated. Now what we've done along this tube here is we have set up an electric and a magnetic field. And the idea here is this. Now let's keep track of the orientations very carefully. What it's saying is that there's an electric field going from the positive plate at the top to the negative plate at the bottom. So inside this chamber that we've set up, we're charging, we're turning up the voltage, we're charging bottom and lower regions, so this is positive and this is negative. Now that means if my charge comes in, let's say it's positive, it's going to get pulled downwards towards the negative plate. So if it were all up to the electric force on this positive charge, this charge is going to get pulled in this direction. It's going to curve downwards. Now what we're also setting up in the very same region is we're also setting up a magnetic field. Now the electric field was oriented downwards. The magnetic field we're going to orient into the page. So we're going to generate a magnetic field around this chamber, and we'll see how to do that in the next chapter. We're going to generate this magnetic field, and the effect of that is that when this charge comes in, it's going to experience a force in exactly the opposite direction as from the electric field. So we've oriented the electric and magnetic fields in a way where we're going to have opposing forces on this charge. And then you have to say, well, who's going to win? Which force is going to pull the charge in its direction? And it comes down to how fast the charge is moving. So the electric force, that's going to be the same value however fast the charge is moving, pretty much. But the magnetic force is directly proportional to speed. So that says if I send through a series of charges, all at different velocities, that the slow-moving ones will end up hitting the plate at the bottom. The fast-moving ones will actually hit the plate at the top. At higher speeds, the magnetic force will be larger than the electric force for the way we've set this up. And so only those charges with a very definite velocity, a very narrow velocity range, are going to successfully make it through the opening at the other side. So this is considered a velocity selector. So kind of interesting, right, that you can use electric and magnetic fields to redirect all of these charged particles, and in this case, only the ones with a particular velocity that we're looking for are going to be, so everything coming out from that opening on the other side, pretty much all those charges are going to have the same velocity to them. Now, just going back to this picture one more time. So what's going on here is, you know, we talk about these fields all the time. It's the magnetic field exerting the force, it's the electric field exerting the force. But you can think of it just in terms of the charges themselves. I mean, when we say there's a magnetic field surrounding the Earth and it's redirecting the charges, what we're really using the magnetic field to represent is the effect from currents of charges down inside the Earth's core. So here are all these charges coming in from the sun, and here are all these charges in the Earth itself, in the planet, down in the core, circulating around. And because all of these charges in the Earth are circulating around, as these other charges approach, they get pushed away and then redirected. They get pushed away, sent into spiral motion, and then spiral into an axial region relative to where these charges are. So it's always charges exerting forces on other charges. So you can always take a step back and go, yeah, but what's generating this magnetic field? It's charges moving down inside the Earth. That's what's exerting forces on these other charges as they approach. Same story here. When we have our velocity selector, we could say, oh, it's the electric field that's creating the force, but what's creating that electric field? Well, there's a bunch of positive charges here, a bunch of negative charges here, and so when this positive charge comes in, it's being pushed away from the positive charges in the upper plate. It's being drawn towards the negative charges in the lower plate, and so that's what's resulting in the force. Now the magnetic field is a little more complicated We'll see this in the next chapter. In order to generate a magnetic field in that direction, what we probably want to do is either get a really big magnet and put this in between the poles of the magnet. Another way we could do that is to get a bunch of current and circulate current around the chamber. If we're circulating current around the chamber, that's going to generate a magnetic field. And so these circulating charges in my wires are going to have an effect on that positive charge coming in. It's going to end up directing it in a particular direction. Okay, so again, kind of interesting to step back and thinking, oh, it really does come down to forces exerting, or charges exerting forces on other charges. All right, let's design an electric motor. What we could do, now that we have kind of an understanding of how these magnetic forces work, let's try this. Let's create a region of magnetic field. So we're going to start off with a magnetic field region. And then what we're going to do is we're going to take loops of wire and place in the magnetic field region, and then we're going to turn on a power supply and run current through those loops of wire. Now, if I've got a loop of wire set up like this, now these wires, they've got to be connected to a power supply somewhere, because what we're doing is we're maintaining current through here. If I look at this particular picture, the diagram we have right here, what would be happening is this. Since I have current in this direction, and I have a magnetic field here, that would say that there's going to be a force going into the page. So all along here, not just that one location, but all along this length, I'm going to have force pushing that into the page, perpendicular to the field. What happens when the current turns and runs along the magnetic field? Now, I don't know if we've mentioned this very clearly, but if I've got current going through a magnetic field and the current runs right along the magnetic field line, it doesn't experience any force. It depends on, it's that sideways effect again. In order to have a force, I need to have a current where at least one component of its direction is not lined up with the magnetic field. So lining something up with the magnetic field doesn't give us any force. So at least with this diagram we have right here, and there's some more diagrams below we'll have to compare with. But looking at this diagram right here, there's no force along the top. There's no force along the bottom. Where the current's moving upwards, there's a force into the page. Where there's current going downwards, again using a right-hand rule, that looks something like this. Okay, current, magnetic field, force is coming out of the page. And so what we've got is we've generated a torque. This is labeled as force 1, this is labeled as force 2. The forces are the same magnitude, but they're in opposite direction. So there's no net force, but there is a torque. So, and that torque is going to tend to rotate that wire loop that we placed inside there. Now, the idea of this, it's basically going to become an electric motor for us. What we're going to do is we're going to attach some axles onto this. We're going to turn up this current. We're going to let this thing spin. Now, in order to see the effects as we spin this, instead of taking this front view that we're looking at right now, what we're going to do is we're going to look at it from the top down. So these next two pictures are looking from the top down onto the motor. So this now is the axis right there. And these are the forces. This is the force 1, that was going into the page. On my top view, it's now oriented this way. And F2 is traveling here. As far as the current directions, that circle with the little dot in the middle, that's saying the current's coming out or upwards out of the page here. And then it travels from left to right, and then it goes down into the page there. So, you know, spend a little time here. And make sure you can visualize what's going on with those diagrams. If you need to, get a set of structures where you can actually look at that and see what's happening. All right, so we've got a force here and a force here. That's going to create this torque. Now, as this thing begins to rotate, the torque is not going to be as large. What's happening is, right here, we have a lever distance that is equal to 1/2 b. There's a 1/2 b lever distance on this side. There's a 1/2 b lever distance on that side. But as it begins to rotate, we get less and less torque. So if we're going to turn this into an electric motor, what we're going to need to do is every time it rotates halfway around, we're going to have to switch the direction of the current. And that's one, it's not every electric motor designed this way, but that's certainly one design for an electric motor, is every time it does a half rotation, you switch the direction of the current. So the current changes direction, and then the torques, the force is reversed, and that means that it will continue to travel around in circles. All right, now let's see how much torque we've got here. The torque we ended up with depends on, now I always leave out the number of loops. So there's always these factors of n that show up. Maybe it's not just one loop, maybe it's 10 loops, or maybe it's 50 loops, or 100 loops. Well, it's going to be the same effect for each one of those loops. So the overall torque depends on how many loops there are, how much current we're running, what the cross-sectional area is, and how large the magnetic field is. And then there's this sign factor, which has to do with how this is oriented. Now, where did the area come from? The B is telling us how much lever distance we have. So little b is the lever distance. A is the length of the wire running through the magnetic field. So I pick up a factor of A from the force calculation, and I pick up a factor of B from the torque calculation, and combined A times B gives me the area. Now it turns out it doesn't have to be rectangular, it can be any shape, area still works. So this tells us how much torque we'll have acting on a current loop made of 8 loops running a current of I with an overall area of A in a magnetic field B, and you can see that's varying with the angle. Now, what we do with that formula is, do you guys remember electric dipoles? There were these electric dipoles that would experience torque in electric fields. So if you look back in chapter 21, there was a pretty analogous setup using electric dipoles in electric fields. And what that formula looks like is it looks just like the torque generated by electric dipoles in fields. So what we're going to do is say, hey, let's define a magnetic dipole. So a magnetic dipole is defined as current running through a loop with area A, and there's a factor of n. If there's more than 10 or 15 or 20 loops, then the dipole has a larger magnitude to it. So this turns out to be really handy. It seems a little funny. It's like, really, we're going to take these loops of current and refer to them as a dipole, but this whole concept of dipole shows up in a number of places, and it's a nice way to unify different effects. So that's our magnetic dipole. Now, with the electric dipole, I think we used a symbol P for that, which didn't make much sense. So we're going to use something here that doesn't make sense either. We're going to use a Greek letter mu for the dipole. And again, the dipole is going to be given by N times I times A. And the word moment always gets tacked on. It gets left off a lot too. A lot of times we just refer to it as a dipole rather than a dipole moment. Doesn't seem to add much information. So here's just a reminder. If you think back, we had an electric dipole effect. And the electric dipole effect, now I'm going to say it made sense. The electric dipole is taking place because they got a plus charge and a minus charge, and they're attached to each other. And when these forces show up, that creates a torque. And so for the electric dipole, it's a plus charge and a minus charge separated by some distance d, and the magnitude of that is q times d. Now, the magnetic dipole, I don't see the two poles. So the only reason we call this a dipole is because it has a set of behaviors that are analogous to the electric dipole. If I place it in a magnetic field, it experiences a torque. There's energy, potential energy associated with the magnetic dipoles and magnetic fields. So the properties match up really well. Now in this case, the dipole consists of this loop. Let's think of that. There's a loop of wire, a current loop, and there's current running through that wire. There's an area that the loop contains. Within that loop, there's a certain area. And then for direction here, we use the area vector. Now, the area vector has come up a few times too, and we just want to remind ourselves that if I have a surface of some sort, the area vector is defined to be a vector that's perpendicular. I guess we saw this in Gauss's law. That was at least one of the examples. And so I'm using a vector to represent the orientation of this loop. And that allows me to define the dipole in terms of the area vector. Now, before with the area vector, we said, you know, it's kind of two possible directions we can define for the area vector. Now, when we have current running around the loop, then what we can do is we can use a right-hand rule and say our fingers are moving in the direction of that current, and the area vector is in the direction of our thumb. You can also think of this as an XYZ coordinate system. So if I were in an XYZ coordinate system and the current, was running through the, let's say this is the x-axis and this is the y-axis, if I've got current running through the xy plane in that direction, then we tend to define the area vector along the z-axis. So it's another one of those right-hand coordinate system definitions. So we'll get more experience with that. We'll see some chances to come back, and we're definitely going to need to keep track of the area vectors for not just for magnetic dipoles, but for other situations also. All right, so here it is, the torque acting on our current loop, and we're going to refer to that as a magnetic dipole. The NIA magnitude is giving us the magnitude of that dipole, and in terms of vectors, again, it's related to the area vector. Now, back in chapter 21 with electric dipoles, we defined electric potential energy, and now we're going to have magnetic potential energy depending on how, and here's our potential energy formula U, depending on how this is oriented within the magnetic field. So let's take a look at this picture right here. If I've got torques pulling on that loop, so I've got a loop of wire, and I have torques trying to orient it so that the area vector lines up with the magnetic field direction. So that would be the lowest potential energy. The torque is always trying to orient the magnetic dipole so that it lines up with the same direction as the magnetic field. I could store energy in that by taking that dipole and rotating it back. So if I take that green vector right there, the area vector, and what it's attached to, and take that loop and rotate it back the other direction, I've stored up a bunch of potential energy. If I now let it go, there's a possibility this thing will rotate back into this place. So the torque is going to tend to rotate it back. So it's a potential energy formula for these, for the magnetic dipoles. So let's try some examples of this. So what they're saying here in this example is that we have what they're calling a coil. So they're saying torque on a coil. Now, it's a coil of wire. It's got 10 loops in it, but the loops are so closely compacted, we can treat it as if it's still flat. So it's as if all 10 loops are in the same plane. So we've got a diameter of 20 centimeters, and it contains 10 loops, and the current is 3 amps, and it's in each loop because, hey, it's the same wire, right? It's all going to have the same current. And it's placed in a 2 Tesla external magnetic field, and they want to figure out how much torque is going to be exerted on the coil by the field. Now we know that at certain orientations there's no torque at all. Once we line up the magnetic field with the direction for the dipole, once the dipole's orientation and the magnetic field are pointing in the same direction, there won't be any torque at all. The way we're going to get the most torque is by rotating it back 90 degrees. So if we get that 90-degree orientation between where the magnetic field is, let's go back and look at that. Maybe here, yeah, maybe here is our best, our best diagram. Then what we are looking at, if we rotate so that the green line again is giving us the orientation, if that green line lines up with the magnetic field, at that point there's no torque. The forces are exactly opposing each other, there's no lever distance, and so there wouldn't be any torque. To get the most torque, we want the diagram right here. So if we rotate, now they didn't put the green vector in, but the green vector should be right there. And then the magnetic field, and what that's doing is it's giving us 90 degrees between the two. The angle acting between the two, that's going to take place at 90 degrees. As far as the torque calculation, for the example, we can put in those 10 loops, we can put in the however many amps of current we were looking at. We need to calculate the area, we need to know the magnetic field, and then for the angle we can put in 90 degrees. So the maximum torque is going to occur at 90 degrees orientation for our magnetic dipole. And that's what we would put into these numbers. So it's 2 Tesla for the magnetic field, it's 3 amps of current, 10 loops. So N times I gives us 30, and times 2 is 60, and we need, oh there we go, we need to do an area from this. So pi r squared. So we're going to get a pi times 0.1 meters squared to determine the torque on that particular coil. All right, here's another example we could think in terms of what would be the magnetic dipole moment of a hydrogen atom. So kind of the same thing. So what we're doing is assuming that we've got, well, we do. In atoms, what we have are the electrons and protons in hydrogen specifically. So we've got a proton, we've got an electron, and they have spins. And it turns out that there's 2 possible orientations. There's an orientation where the proton and the electron spins match up, and there's where the proton and the electron spins are opposite. Now, the magnetic effects, each of these particles, the protons and the electrons and even the neutrons, we said, behave as a magnetic dipole. So we don't think of them as having little loops of current, but at the same time, we do think of them as charge distributions that have angular momentum. So the effects are quantized, and that says that an electron has a particular predicted amount of angular momentum, has a half unit of spin, and along with its charge determines how much of a magnetic dipole it will have. So we can go in and make predictions about magnetic dipole effects with protons and electrons and such. All right, let's move on and let's look at a couple of items that we've talked about here. Motors, that's certainly an important application. We said that those loops of wire placed in a magnetic field create an electric motor. So here is the current loops that we've set up in the rotating portion, which is referred to as the armature. And then we said that what has to happen is every time we go halfway around, we want to reverse the direction of the current. And so here are contacts, these brushes, and so every time it makes a half rotation, the contacts reverse. So there's contacts coming in from the outside, from our power supply, and then there are contacts on the rotating portion, and every time it rotates halfway around, the direction of current ends up being reversed, and that's what keeps the motor rotating. So this is kind of a detailed, I guess. Here's our battery, it's a DC power supply, and we're connecting that up to these two contacts, and then the armature is placed in between those. So kind of a diagram as to what our electric motor would look like. Here's another example of using these magnetic effects. And what we have here is we've got a speaker wire. So we have the wires leading in to the speakers, and as the current varies, what happens is we increase and decrease the magnetic fields that are inside here. So the speaker has magnetic material in it, and so what's happening then is the speaker is pulled in and out through this magnetic field as the current comes through. So the current's coming through here and it's getting pulled in a particular direction back and forth. So what happens then is, hey, if we want the speaker, so the speaker is a mechanical device, there's a piece of flexible material in there vibrating back and forth, and we can pull that material back and forth. We can control the vibrational frequencies by running an electric current into that. So if we can get an electric current that has the same pattern to it as the sound that we want to generate, that's enough. That's enough so that we can go in and get that speaker to operate and generate sound for us. So converting an electrical signal into a mechanical signal. Okay, one item, maybe our last item for this chapter, is looking at a mass spectrometer. So what we've got here are a couple different, well, let's see what's going on. A mass spectrometer, first of all, the idea is that I can take some chemical compound. You know, maybe I've synthesized something in the chemistry lab. I'm not sure what I've synthesized. I'm wondering what kind of clues I could get as to what this new material is. One item we might think about doing is sending it through a mass spectrometer. What a mass spectrometer does is it starts out by ionizing the sample. So it will pull electrons off the sample so that they acquire one positive charge. Now that gives them a well-known amount of charge And then what we can do is there's a couple options here. One thing we can do is we definitely have to speed them up. So we're going to have something that accelerates those charges through some kind of a potential. So we're going to take those positively charged molecules now that all have the same, that have a particular mass to them. We're going to send it through a velocity selector, at least that's what we have outlined here. So in the velocity selector region, we have, magnetic and electric fields that are turned at right angles to each other. What we saw in the earlier example is that if that's the case, then let's generate a bunch of these particles moving at a variety of speeds. And then what the velocity selector will do is it will allow us to select for a particular speed. So we can adjust the voltage over here until those molecules have the right speed so that they're able to get through the velocity selector portion of the device. Okay, so if they get through the velocity selector, then what that tells us is all the molecules coming out of here are moving at the same velocity. So now in the magnetic field region that we've set up over here, that was the velocity selector region had magnetic fields and electric fields to it. But over here now, it's a purely magnetic field. And what happens is that these molecules, since they've acquired a positive charge, we've ionized them, we've taken off one of their electrons, they're going to follow a circular path. Now the radius of that path is going to depend on what the mass is of those molecules. And so that says that if it's a heavier molecule, it will follow a larger radius, maybe it hits down here. If it's a lighter molecule, it will have a shorter radius and maybe it hits down here. And then what we have is we have a detector. So we have some kind of detection device along here to find out where the molecules are landing, and where the molecules land tell us what the radius of curvature was for those molecules. And if we know what the radius is, we can use our formulas to work back and determine what the mass was. So that's kind of interesting, a way to determine just masses of individual molecules, or a sample of molecules. We can collect those molecules and determine what their mass values are. Now, when the first nuclear weapons were being developed back during World War II, researchers were trying to figure out a way that they could sort out the two isotopes within uranium. There's a uranium-238 isotope, there's a uranium-235 isotope, and this has been in the news, this is kind of in the news even today with nuclear weapons development, is that you can use different types of devices to sort out these different isotopes. Well, one of the original ways to sort out isotopes of uranium-235 and purify the uranium-235 is to use mass spectrometers. So if you take naturally occurring uranium, it's more than 99% uranium-238. Uranium-238 does not reliably undergo fission reactions. And so what does reliably undergo fission is the uranium-235 isotope. Now, uranium-235 makes up less than 1% of naturally occurring uranium. And there's no chemical reactions that are going to determine the difference between uranium-235 and 238. Chemically, they behave identically. There's just this small mass difference between them. So one of the techniques that was used were mass spectrometers. So the government built, thousands, tens of thousands of these mass spectrometers, and people operating these mass spectrometers, I guess they had classified status, but they really didn't understand for the most part what it was that they were doing. But you could you could send these through, and the uranium-238 was a little heavier. It would land at one location. The uranium-235 a little lighter, and it would land at slightly a different location. And then you could collect the uranium-235 from its location, and it would be enriched. And then you would carry that process out over and over and over. There were at least tens of thousands of people, I believe, if I remember the numbers, sitting at these machines just trying to come up with a few kilograms of uranium-235. So mass spectrometers, really handy devices. They let us go in and measure masses of different molecules. So here's an example that they have come up with for us here. It says that we have a sample of carbon atoms. Now the carbon atoms individually have a mass of 12 atomic mass units. So the molar mass on carbon-12 is 12 grams per mole. It's found to be mixed with another unknown element in a mass spectrometer with a magnetic field V prime. It says that the carbon ends up going through this circular path, and it has a radius of 22.4 centimeters, whereas this other unknown material is coming in at 26.2. And what they're doing is they're asking, hey, what's the unknown material? The assumption here is that all of these have been singly ionized. So when we ionize the sample, everything gets one electron pulled off. All right, so it should be enough to work from these ratios of, or the ratio of the radiuses, and knowing the original starting mass here of the carbon. Let's see how we might come up with that. Now, I actually did this. I did a different version of this up above. What I did was I did their problem down here. So what I said was, look, I did use this formula right here, which we had derived earlier. That's the radius for a charged particle moving through a magnetic field. And the radius is going to depend on mv divided by qb. Now, what they're assuming, since they put a velocity selector in their mass spectrometer, they had it built where there was a velocity selector built in. If everything's coming through at the same v, and every molecule has the same q, and everything's going through the same magnetic field, then what that says is I can write that equation down as a ratio. R2 divided by R1 is the same thing as M2 over M1. I put a little question mark here because this would only work if we had that velocity selector in place. And what I outlined here was an example not using the velocity selector. So it's a little different. Anyway, let's start from that assumption that I think they intended for us to use. And what that would lead to then is M2 is equal to M1 times R2 over R1. I put the numbers in, and it said the mass of this unknown material is 14. Now, what would have a mass of 14? And you think, well, if we're looking at individual atoms, it could be nitrogen. You know, nitrogen's most common isotope has a mass of 14. Maybe that's nitrogen atoms. Also, there is a carbon-14. There's an isotope of carbon at 14, but that's really rare. It could be somehow some of this radioactive carbon-14 is mixed in with the rest of the carbon. And, but they didn't mention carbon-13, so carbon-13 is another isotope of carbon that's actually present in naturally occurring carbon. So anyway, carrying out this number gave us 14.0 atomic mass units. Now, there's a more general way of looking at mass spectrometers. What we can do is this. Instead of using a velocity selector, what we could do instead is use the same voltage to speed up all of the molecules. Now, the disadvantage here is that if I just use the same voltage, then not all the molecules will acquire the same speed. The heavier molecules will not speed up as much. By sending all of these molecules through the same voltage, they're going to end up with the same kinetic energy. So what we can do is say each one of the molecules, the heavy ones, the light ones, the in-between ones, they're all coming out with the same kinetic energy, 1/2 mv squared. Some of those are going to be going faster, and some are going to be going slower. So what I did was I solved for the velocity and said, look, they're coming out through the accelerator region of my mass spectrometer at different speeds, but I can figure out what that speed is. I can write down a formula. The speed's going to depend on, well, it's going to depend on how much charge they have, which we're assuming is one fundamental electron or proton charge. Whatever voltage I have the accelerator turned up to, divided by the mass, square rooted. So I can get an expression for V. Now, let's go back up to this point. Now, in this example, where we're not using a velocity selector, then the molecules coming out are all coming out at different values of V. So I can't use this ratio. I have to do a few more lines of algebra. So what I've done here is, in place of V, I wrote in this expression in terms of the charge, the mass, and the voltage. So this fancy V up here, that's voltage. So my radius then, when I solve this, I put the V in here, and then the next line I'm solving for what the radius would be. What I'm finding now is that the radius is not directly proportional to mass anymore. It turns out that the radius is proportional to the square root of the mass. But we can still set up a ratio. So if I take out the velocity selector, I'm not using this expression anymore. Instead, I'm using this. Okay. Now the advantage here is, if I don't use the velocity selector, then all my molecules make it through. Rather than having only a certain set of molecules make it through to the other side, I can get all the molecules to come through. So this way, I get a much more intense beam of molecules that are coming through. And you know, the downside was, or the upside is, I got to do a little more algebra and figure out what the relationship would be. So I went back and solved it this way, assuming that it was this kind of more general, robust type of mass spectrometer. And when I did that, I got a mass of 16.4. Now, what do you guys think? Is a mass of 16.4 atomic mass units sensible? And it's not, right? If we get down to the level of molecules, the molar masses have to be integer values. If I'm getting a number that's not close to an integer, it's probably got to be some kind of a mistake. In the example where I assumed there was a velocity selector, the answer came out to 14.0. That looked really good for a mass of an atom. There are going to be atoms or molecules, possibly molecules, maybe something. I was thinking if maybe methane, no. Anyway, but 16.4 becomes a problem. Now, you may be aware that on the periodic table, there are a few elements. Chlorine, for example, comes in with a mass of 35.5. And you're thinking, is that really the mass of individual chlorines? And it's not. So what happens in these mass spectrometers, let's say that we took a sample of naturally occurring chlorine. Well, chlorine's made up of two different isotopes, chlorine 35 and chlorine 37. So even though we average them when we're measuring out chlorine to run a chemical reaction, because we know we have a mixture of isotopes, something like a mass spectrometer is going to separate out those two different isotopes. So that says, hey, the chlorine 35s are going to land at one location, the chlorine 37s at the other. So there shouldn't be, none of my answers should be coming out to something that's kind of like a half integer. Everything should be coming out near integers. So I'm pretty sure they intended us to use this approach with the velocity selector in place. Anyway, just something to point out with the calculations that we have here. All right, we're going to wrap up chapter 27 here. So it's a lot of new stuff. We've introduced magnetic forces and magnetic fields. Now we have another chapter ahead of us, and we're going to be looking at primarily magnetic fields more carefully. But these are kind of the big formulas that we ended up with. There's a series of slides here. First of all, a couple things to point out. Magnets have north and south poles. I'm going to say, when you think about magnetic forces, the first thing that comes to mind should not be a magnet. I know that's hard, but magnets actually have some complexity within them, right? So I'm going to say, if you're thinking about magnetic forces, the first thing you should think about are point charges in motion. If I have a charge and it's moving, I'm going to get a magnetic effect from those charges, individual charges. Now magnets are complex objects. They have all those electrons spinning inside, and the effects of magnets are due to spinning electrons. Electrons have angular momentum, they have charges, they're going to demonstrate magnetic effects. We can define poles, and the north repel and the south, but again, what that's coming down to are two electrons spinning in the same direction, kind of lined up. There's actually going to be a magnetic effect that draws them together. We'll see more of this in chapter 28. Or I guess we've already seen it. Let's go ahead and point that out. What we had looked at were two charges moving side by side, or two wires of current moving side by side, and said that the magnetic effects would draw them together. That's what's happening with the electrons. If you think of the electrons spinning as loops of wire, they're like little pieces of current moving together in the same direction, and they draw towards each other. That's why north and south attract on magnets. If the electrons have spins in opposite directions, which I can't demonstrate, but I'll just do this pretending to. So if you can't figure out what I'm doing with my hands here, it's because it makes no sense. If they're oriented opposite each other, then they will repel. Okay, so that's like south and south, or north and north. The unit of a magnetic field is a Tesla, and I want to say that's a little artificial. We're going to kind of go back and forth between measuring magnetic fields in Teslas, but there's also times we'll see when we want to measure them in newtons per coulomb. And we do that by adding a factor of C out front. We talked about that a little bit early in this chapter. Electric currents generate magnetic fields, and you go, well, yeah, of course, because electric currents traveling in wires, those electric currents are charges that have a velocity to them. And then finally, magnetic fields will exert forces on other charges that are moving by. So basically, I got a charge here, I got a charge here. How do I get them to exert magnetic effects on each other? And they both have to be in motion. If only this one's in motion, it will generate a magnetic field, but that one won't feel it. Same thing if this one's in motion. If they're both in motion, then this generates a magnetic field, and this one moving through the magnetic field feels the effect. And this will generate a magnetic field, and this one will feel it. So now, because the motions could be sort of random, it turns out that the forces are not necessarily equal and opposite. So we'll see examples where the magnetic forces of charge 1 acting on charge 2 don't match the force of charge 2 acting on charge 1. Again, kind of interesting that that effect takes place. All right, here's my favorite formula from the whole chapter, is that one. I'm going to say this chapter primarily is looking at magnetic force. And the fundamental equation for magnetic force is how much force does a charge moving with velocity v experience in a magnetic field. There's a couple of dipole moment equations down here that you should be aware of. Take a look at the homework problems with those. But I think it's the one at the top from which everything else can be derived. All right, questions on chapter 27. So we'll close it there, and next class we will be moving into another magnetic chapter. We'll be looking into chapter 28. And again, if I had to kind of label these, I would say chapter 27 primarily looking at forces, chapter 28 primarily how do we create magnetic fields. Okay.